Hi everyone, my name is Saket. My topic in this subject is electric currents through ion tracks in silicon devices. So let's get into electric current. An electric current is a flow of charge from one place to another. The unit is ampere, which equal to a flow of 1 coulomb per second. So, here is the diagram for the given information. Damaged region of cylindrical shapes called ion tracks, typically in nanometers wide and tens micrometers long, are formed along the ion trajectories in many insulators. When high energy ion in the electronic stopping region are injected, effects can occur in semiconductor device when an energetic charge particle moving through the device creates a column or track of mobile electrons hole pairs. These carriers can produce currents via drift diffusion (DD), which may lead to an unwanted device response. The simplest and most familiar illustration of currents produced by ion tracks consists of a reverse-based silicon diode containing a junction depletion region above a uniform doped quartz neutral substance, as shown in figure. Carriers liberated by an ion track produce a current through the diode, which can sometimes create unwanted effects in external circuits that respond to the diode current. There are, of course, differences between a traffic jam and charge transport. However, whatever we are discussing, cars responding to traffic, carriers responding to drift diffusion, it is still true that density and flow are different quantities. And if flow does not require a charge in density, as previously stated, the ambipolar diffusion equation may describe the carrier density function, but says very little about carrier flow. The present paper goes a step beyond Feldman's discussion by deriving a modified form of Ohm's law, which does say something about carrier flow. Also, a fairly completed description of charge collection from ion tracks in silicon diodes is discussed quantitatively. So now let's come to the limitations. Several sources of uncertainty should be acknowledged. The analysis to flow is based on the DD equation in a uniformly doped quartz neutral silicon substrate. It could be argued that the DD equation may be inadequate for the extreme conditions, large carrier densities and density gradients, typically of an ion track. If true, this would have far reaching implications regarding nearly every computer simulation to date of charge collection from ion tracks, while some of the more recent computer codes utilize transport equations that are more versatile than the DD equations. Most simulations to date are based on these equations. However, it is acknowledged that these equations could have limitations. Is acknowledged that these equations could have limitations. Another source of uncertainty is the Einstein relation used to calculate the diffusion coefficients of mobilities. Another accomplishment is that the quadratic Poisson equation may have some limitations if transits are too fast. This equation contains a well-defined low-frequency dielectric constant and may not be appropriate when transients are too fast relative to the dielectric relaxation time. It is not the intention here to resolve above issues. The issues are mentioned only to acknowledge that the results presented here may have limitations. The DD equation, the classical Einstein relation, and the quasi-static Poisson equation are the postulated equations for the analysis to flow. Before starting an analysis applicable to quasi-neutral region, it should first be pointed out that such region exists according to DD equation, at least for one simple device illustrated in figure 1. One of thing learned from computer simulations is that even in the presence of a ion track, silicon diodes having a uniformly doped substrate show a reasonably well defined DR boundary (DRB) separating the DR, a strong space charge region, from a quasi-neutral region. The latter region is defined by the property that the charge imbalance, measured as density of elementary charges, is small compared to the majority carrier density. Here is a diagram of electric currents through ion tracks. So let's get into the future application. An anticipated future application of and an primary motivation for the present work is to improve the accuracy of an earlier, simple but crude analysis of charge collection in diodes. The analysis, which is limited to high density conditions, the carrier density greatly exceeds the doping density. The density generally exceeds the doping density of the carrier density function at the DRB by solving the ambipolar diffusion equation, and this gradient is the use to calculate the majority carrier diffusion. The analysis neglects DRB motion and equates total curve to twice the minority carrier diffusion. Now let's get into the summary. This work is intended to assist a future theoretical modeling effort by providing one quantitative relationship which is necessary, though not sufficient, to determine how a device voltage is divided between distinct regions. This is which relates the carrier density and potential to the current through the quasi-neutral region. This equation includes all currents, electrons and holes, drift and diffusion. While this one relationship is not enough for a quantitative analysis of a complete device, a fairly complete quantitative discussion was given for charge collection in diodes. Thank you, hoping you understood my information.